Hello, my name is Evan Cardenas, and today we're going to be talking about Lab 2, which is a continuation of Lab 1, which in layman's terms just sees us charge pieces of clear tape. It sees how they interact. The idea is to see how the tapes behave with each other and with other objects, like a rubber pin. We'll also estimate how much charge ends up on a tape, assuming it's spread evenly along the length, and we'll use glow soup to visualize this. What are we going to try to do? We're first going to charge two tapes and watch them attract or repel. Second, we're going to see how they react to other objects, like your hand or your pen. Third, we're going to figure out how much charge on the tape, and we'll show this in the glow script. So there's four big concepts. The first is, of course, Newton's law, which is net force changes momentum. Pretty simple. Gravitational force, arguably simpler, which is just the downward force equals F equals mg. Coulomb's law, the electric force between 2 point charges, F equals K Q1 Q2 of R squared. Um, and line charge model, which is essentially just point charge, except it's evenly distributed along the length. I would say the equation, I butchered it every time, and then it ends up snowballing, so I'd rather spare you that, but you can see it. Before starting, we need some reference values. Each tape is 0.2 meters long and 0.019 meters wide. The weight of one tape is 0.00196 newtons, and the area is 0.0038 square meters. This is the distance between the two tapes, about 0.013 meters. We'll use these numbers for both the calculations code. So here's what we're going to do in the experiment. First tape one tape on the table, then tape another one onto the last one. Ooh, remove the second tape from the first tape to recharge it. Repeat again and see how they interact with each other. Redo steps 1, 2 a lot. Then observe how that tape interacts with the pin rubbed on the cloth to negatively charge it, of course. Get two charged tapes and tape one onto two different objects. Form your bridge. Place the other tape below this bridge and observe how they interact, and then note the distance. Um, what we observed. Tape one was attracted to the hand and pencil, showing its positive charge because the pen is negatively charged and the hand is neutral, so it'd still be, you know. When we bring the two tapes close together, repel each other with on the bridge, the fixed tape moving away. These interactions tell us all about the force and the charge on each tape. Our measurements for lab 1 show that a charge tape is a net positive charge of about 6.07 times 10 to the negative ninth coulombs. This means roughly 3.79 billion electrons are lost. Using the uniform distribution formula, the line, the total charge of the tape is about 4.62 times 10 to the negative 7 coulombs. With the ratio of electrons lost to atoms comes out to just 1 electron per 1 times 10 to the 7th atoms. So code. This part is just force of constants. In this part, we define constant in code. Coulomb's constant, K equals 9 times 10 to the 9, the gravity 9.81, along with the ones we've already previously defined. We also input the, previously defined stuff. Then we define a function called E field, which calculates electric field at a point from a charged particle, which helps us figure out the force in each small part of the tape. To model the tape more realistically, we break it into small point charges using the line charge function. Each tiny charge is the fraction of the total charge and mass. By using many along the tape, we approximate a continuous line of change, which matches how the tape actually behaves. We create top tape and bottom tape using line charges at their positions according to the experiment. For each point in top tape, the code calculates the electric field from all points in bottom tape. The code also draws arrows, green for electric field, white for net electric force, and yellow for gravity. Finally, the code prints the magnitudes of the forces. And yeah, this is just, you can see they're roughly equal. There's the force, distributed across the tapes. Yeah, it's all on the top one because that was the one that was actually moving. So assumptions made, first that the two tapes are evenly distributed. There's going to be some difference, obviously. There's no air resistance. They both have the same charge and no charge loss when the tape's handled. Possible sources of error. I mean, I could probably guess from the assumptions, actually. The first, of course, being just wrong measurements of length, width, and separation distance, tape not being parallel to each other, and all the reasonable opposites made that you can make from the assumption. Discussion question 1. What if we model each tape as a single point charge? Then the estimated charge is 2.06 times 10 to the negative 7c. With the line charge model, it's 4.63 times 10 to the negative 7c, more than twice as large. The difference happens because a point charge concentrates all the charge in one spot, which is a stronger field, so less total charge is needed to produce the observed force. The line charge model spreads the charge out, so more total charge is needed. Sorry for stuttering. I have to kind of rush a little bit. These estimates differ. Why do these estimates differ? Which value is more likely to be close to the real value, and why? These estimates differ because of the way the charge is modeled. The real tape is charge spread along its length, so the line charge estimate is close to reality. The point charge model is only accurate when the distance between tapes is much larger than the tape